We're going to do some review of double and triple integrals through some problems that we have prepared. And I don't want to do them in the order that they came in, but more in the order that you have more pressing questions. Somebody asked me to start with some number 7, so I'm going to do that. So I'm going to start with this ice cream cone. We want to find an integral. It's not just the volume, but an integral of the coordinate z squared dv over a region that resembles an ice cream cone, because we have this function z equals the square root of 3x squared plus y squared. Yes.
Integrals, are they just going to be set up? Because I noticed a lot of them are just setups instead of like the value.
Yes, that's a good question. So we are very interested in you being able to set up integrals. We're interested in that you are able to do integration, but that was basically a lot of the material of Calculus 2 was compute integrals. Here we're more interested in the setup of 3D integrals, understanding what the region is, describing what the limits of integration are describing, and then how to set it up. So there will be problems in the exam where you have to evaluate the entire integral, but there will be a bunch of questions like this one where it's just set it up. And setting it up means I want to see all the limits of integration. I want to see the order of integration that you are choosing correctly. And I want to see, in this particular case, we're going to use the spherical coordinates. So you have to use the correction factor, the Jacobian of this transformation correctly.
Yeah, I saw some of them too. Do you want us to show graphs as well?
If it says so, I mean, it is always helpful for you. It is helpful for me to draw something here to just follow along of what I'm trying to do, especially to set up, if I'm going to set up in Cartesian coordinates or in the spherical coordinates, a graph helps me decide what the limits of integration are going to be. So it helps me. So sometimes it will just help you. You don't have to graph it, but in some other cases, it will say sketch a region, and then that is part of the points in the problem. So z equals the square root of 3 times, so z equals the square root of 3 times x squared plus y squared is a constant times the square root of x squared plus y squared, which is a cone, but the constant just changes the sharpness of the cone, okay? So in this particular case, I'm just going to sketch it like this. It's some cone, okay? And then there is a sphere on top. So the sphere will sit, hopefully, something like this. Okay? And I have to do the integral in the region that is above the cone and within the sphere. So it does look like some sort of ice cream cone. Okay? So I have to figure out, I could try to set it up in Cartesian coordinates, but that is actually making my life more difficult. I can just try to do it directly in the spherical. So what I need to know is what are the bounds for rho, what are the bounds for theta, what are the bounds for phi. So what are the bounds for phi? Remember where the positions of those three, just change this one. Where are, just remember the spherical coordinates, where are these angles and lengths? If I have a point here, and this is the point theta phi rho, say, then this length here is rho. This angle from the z-axis in this direction, that is phi. And then if I project my point down to the xy plane, and I trace the line from here to here, then the angle from here to here, that is theta. Okay? So I can see right away that 1, theta is 0 to 2 pi, because I am not restricting, the setup doesn't say the region of the cone that is just in the first octant, or that is between like x, y, and z are all positive, or it's not cut out by, it doesn't say anything like that. So it's entire, the angle here, it goes from 0 to 2 pi. Great. I need to know what happens with phi. By the way, rho is also not difficult to see, that rho can go, if I am within the angle phi, and for any theta, I can go from here up to the sphere. So let me just say what I just said out loud, that first of all, theta I know is going to go from 0 to 2 pi. That phi, or that rho, is going to be able to go anywhere up to it hits the sphere. The sphere is of radius 2, because it's 4, it's the square root of 4, so the radius is 2. So rho is just going from 0 to rho is going from 0 to 2. And now I have to figure out what is the limits for phi. How do you suggest we figure out what is the limits of phi? So you're already using some of the transformation in the spherical coordinates. Let me give you a more pictorial view, which is why I like drawing this myself, because what I'm going to see is if you cut out my cone just in the YZ plane, I can see the cross section of the cone, and I can see how wide it opens up. Okay? So in that plane, which is the YZ plane, what is happening in that plane? The YZ plane, by the way, is the plane x equals 0. So let's graph those things in the x equals 0 plane. So I have the sphere becomes y squared plus z squared equals 4. So it becomes a circle of radius 2. Okay? And the cone, the equation for the cone with x equals 0 becomes z equals the square root of 3y squared, or the square root of 3y. Okay? And, well, not right, because this has to be the absolute value of y. If I do the square root of y squared, I get the absolute value. And then what I get is something like this, where these lines are z equals the square root of 3y and z equals minus the square root of 3y. So now I need to know what is this angle from here to here. All right? So let me move on to this page and draw that again. This line is y equals z equals the square root of 3y. And I need to know this angle over here. Okay? But if I draw, for example, the number 1 here, if this is 1, I have a square root of 3 there, and now I can use trigonometry. For example, I can figure out that this angle here, this angle, let's call it alpha. What is the sine of alpha will be? Well, actually, this point is the point 1 square root of 3. So this length, the hypotenuse in that triangle is 2, because it's the square root of 1 squared plus square root of 3 squared, so the square root of 1 plus 3. So it's the square root of 4, so it's length 2. This length here is a square root of 3. This length here is 1. So the sine of alpha is the square root of 3 over 2. The cosine of alpha is 1 over 2. So what is alpha?
Pi over 6.
Alpha would be, no, pi over 6, so 30, would have sine equals a half. So alpha itself is 60 degrees. The one I was interested in will be the complement of that. So the maximum phi that I can get is 30 degrees, which is pi over 6, which is maybe what you were thinking about. Okay? So this angle from here to here is pi over 6. And that tells me the final bound, which is that phi can go between 0 and pi over 6. Okay? Any questions of how I found that out? So now I can set up the integral in my polar coordinates. By the way, let me remind you, I'm going to need what the z coordinate is in polar. So as a reminder, you can bring a note sheet to the exam. And as a reminder, x is rho sine phi cosine theta. Y is rho sine phi sine theta. And the z coordinate is rho cosine theta. The Jacobian for this transformation is rho squared sine of phi. And therefore, this triple integral over this thing, this ice cream cone, will be, let's start with theta was going from 0 to 2 pi. Phi is going from 0 to pi over 6. Rho is going between 0 and 2 up to the radius of the sphere. Then I need z squared. From here, z squared is rho squared cosine squared of theta. So I get rho squared cosine squared of theta. The last integral was about rho. And I have to multiply by the spherical coordinates Jacobian rho squared sine of phi. So all in all, inside the integral is rho to the 4 cosine square of theta sine of phi. Okay? And I'm not going to evaluate it, but this is not a difficult integral because the limits are just, the limits of integration are all numerical. And in fact, the rest of the integral is decomposable into 3 different integrals because it's a product of a function of rho times a function of theta times a function of phi. So you can do each one of those integrals with respect to the bounds separately and then multiply all 3 things together to find the value. Yes?
When you have to finding the angle of phi, how did you know that the square root of 3 was the height?
Here, so did you follow up to this point that this line is z equals the square root of 3 of y? Yeah. Then what I did is here is y, and here is z. This is the yz plane. And then I just pick, I need a triangle. So I picked y equals 1, which is the easiest number. So I picked 1 here. And then if y is 1, z is the square root of 3 times 1. So this length, at that point, this point has to have coordinates 1 and square root of 3 because it's on the line. And now you know this length, that length. You can compute the hypotenuse using Pythagoras theorem. And now you have a full triangle. Or, I mean, I computed, my head works better if I look at my triangles here. But you could have done directly this angle here by doing trigonometry on this triangle, which is equivalent. But instead of this angle, you're computing actually this one, which is the complementary angle. Very good. Any other questions about number 7? Yes. It would still be, actually, it would still be, there would be a function of theta, which is just 1, times a function of rho, which is rho to the 4, times a function of phi, which is cosine square phi sine phi, which actually is even easier than just cosine square, because that is a u substitution would do that pretty easily. I looked at my cross section of my object with the YZ plane. So I just looked at all of them basically, but basically what I needed was the cone. I just need the how open the cone is, and therefore I was just looking at the cone, the equation of the cone. So in here, in both these equations, I was first, this one came from evaluating this at x equals 0. So in that plane, that is the plane x equals 0, if you just simplify the equation of the sphere with x equals 0, you get a circle, y squared plus z squared equals 4. This equation with x equals 0, I get this equation, which is the square root of 3 times the absolute value of y. So this is now these two different lines, and I took that one to see how open the cone was. Sounds good? All right. Any other problem that you want me to work through? The bounds for theta. The bound for theta, because the object has full rotational symmetry. So what that means is that it is not a section of this cone, but it's the entire cone. Then theta, which is if you project to the x, y plane, what points do you get in the x, y plane? And in fact, what angles can you get in the x, y plane? Because it's the entire cone, and I can go 360 around the cone, theta has to go from 0 to 2 pi. If it was just like a fourth of the cone, then it would go from 0 to pi over 2. No, I did not assume that. I just used the graphs that they told me, that and that, to actually draw what the figure looks like. So that, I mean, the cone could have been, if the variables were different here, the cone could have been in a different direction, and then it would have been a very different problem.
But if, let's say,
it would have worked anyway, because regardless of the radius, this line, maybe the cone would have been here or smaller or larger. It doesn't matter. What matters is like what line this is. It doesn't matter where the sphere lands in here. I could have still used, this angle is the same here than it is here. So the length of rho does not matter. Yes? Can you say that again?
You just do arctan or
Yeah, I mean, there are several ways of doing it, and I don't know exactly if that is the right transformation, but there's a way to get from x, y, and z. There's a way to get the phi. So you can definitely use some trigonometry to figure out what is the tangent of phi or something to find the value, the maximum value of phi. Yeah. Okay, let's move on to another problem. Let's do something else. What other problem do you want me to do? Number. The last one? Okay. So we want to do a change of variables where R is, they say, a parallelogram in the xy plane. We're going to transform it and then use a linear transformation that brings me from one place to the other and figure out how to do the integral with respect to these new variables, u and v. So first of all, I need to figure out what this other region is, so how the regions are being transformed. So let me first sketch in the xy plane what is happening. So in the xy plane, we have the lines x plus y equals 1. That's y equals 1 minus x. If I put here 1 and 1, it's this line. Okay, so this is y equals 1 minus x. X plus y equals 3 is also a line of slope minus 1 that goes through 3, 0, and 0, 3. So if I do 1, 2, 1, 2, 3, it goes like this. Okay. Then, so this one is x plus y equals 3. Then I have x minus y equals 0. That is the main diagonal. And I have x minus y equals 2. That is a line that goes, this one is y equals x minus 2. So it starts at, when x is 0, it's minus 2, and then it just goes like this. Okay, this is not accurate. It looks like that. So the region R is here. Okay, if you find the intersections of the points at the intersection, it's convenient to find what are the points, because those points are going to be sent to the corners of the new region. So it turns out that I computed this line. By the way, this line here was x minus y equals 0, or y equals x, and this one was y equals x minus 2. So you can find the intersection of two lines easily, and these points are 3/2, 3/2. This point here is 1/2, 1/2. This point here is 5/2, 1/2. And this point here is 3/2 minus 1/2. Okay? So now I can figure out what are the u and v coordinates that correspond to this. So one thing I can do is, first of all, I have my transformation. And I can actually solve for u and v, just to see what is the inverse transformation. So I can find coordinates in u and v out of x and y's. If you do this, just solve for u and v. You solve for u in one, plug in the other. I'm not going to do that here, but you get x plus y and x minus y. So what is happening to those coordinates in the u and v world is that now I get, let me draw the points here, 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 and here. 3/2, 3/2 will go to, if you do x plus y, that will be the u coordinate. 3/2 plus 3/2 goes to 6/2, to 2. And 3/2 minus 3/2 goes to 0. So this point here is mapped to 2, 0. Okay, let's call this A. A went here. Now, where does six halves is 3? It goes here. The new point in the UV coordinates will be 3, 0. I did here, for example, 3/2 plus 3/2 is 3. And 3/2 minus 3/2 is 0. So that point goes to 3, 0. If you look at the point, let's say B, where does B go? B go 5/2 plus 1/2 is 6/2, which is 3. And 5/2 minus 1/2 is 4/2, which is 2. So it goes to 1, 2. So it lands here. Now, B goes there. And then you can see that this point, C, goes to 1, 2. And this point, D, goes to D is 1/2, goes to 1, 0. Okay? So if you now look at the lines, so if you take the entire line y equals x, where does y equals x go? When y is x, u is 2x, and v is 0. So it's the line y equals 2x, or the line v equals 2u. Okay? So this line here goes to this line here. So it turns out that eventually, if you look at all the limits, this is the new region. Okay, it matches that if this was R, this is S. So what that tells me is that my new integral is going to be in this nice rectangle. Notice that the integral over this region is really messy. I can't integrate with respect to x. If I integrate with respect to x first and then with respect to y, I'm going to have to break it into two different integrals. And if I integrate with respect to y and then with respect to x, I'm also going to have to break it into two integrals. So in Cartesian coordinates, integrating over this region is a mess, but in Cartesian coordinates in the uv world, this is u and this is v, in the uv world, that integral is going to be easy because I can integrate, for example, with respect to u between 1 and 3 and between 1 or in between 0 and 2 in v and be done. Yes?
On the exam, are we going to have to choose the transformation, or is it going to be given to us like that?
I can't say. But I think if on top, as you see, there is already some work to figure out even what the region is. If on top you have to figure out a transformation, I think that's beyond the scope of an exam, at least. Okay. Yeah. Yeah.
Can you go over again how you got u equals x equals y?
Sure. Let me just do that. Maybe here I have some room. The transformation was the original transformation that is given to me. Was x is u plus v divided by 2, and y is u minus v divided by 2. Is that right? Yes. So if you solve for u here, u would be 2x minus v. And if I plug in here, then I get that y is 2x minus v divided by 2. So that tells me that y is x minus v, and that tells me that v is x minus y. And then I plug in here, if v is x minus y, then u is 2x minus x minus y, and that is x plus y. So now I have my inverse transformation that u is x plus y and v is x minus y. How do you know? How do you know those bounds? You said from the statement. Yeah. How am I going to know that I have to integrate in u between 1 and 3? That's the problem. That at the very least you need to know what are the possible bounds in you somehow need to know how u and v are going to move before I can integrate, because in the integral in u and v, I'm going to have to integrate over a region, and I have to figure out what are the possible limits for u and what's the limits for v, which are not given in here. If the problem gave me the region S, that would be one step less to do in the exam. Okay? Yes?
But doesn't it give you the region S? Because u equals 1 and u equals 3, so it's between 1 and 3.
How do you know that u equals 1 and v equals?
X plus y equals 2, so u equals 1. And then u equals 3. And then v equals 0, and v equals 2. So it's the interval between 1 and 3 and 0 and 2.
Yeah, so this is a different way to figuring out. You are figuring out what are the limits of integration. It's not given. You're plugging in the limits of those lines, right? You're saying, okay, suppose that x plus y equals 1 and x plus y, you're putting some limits yourself to what things can be, to figuring out what the limits of integration can be. Okay? All right. So now, what is the next step to set up the integral in the u and v variables? I have to find the Jacobian of the transformation. Okay, so now the second step is finding the Jacobian. And that will be the derivative of x with respect to u, which is a half, the derivative of x with respect to v, which is a half, the derivative of y with respect to u, which is a half, and with respect to v, which is minus a half, and that is minus a fourth, which is minus a half. In the formula, though, for the transformation, we use the absolute value of the Jacobian. So typically, you are going to do all of that work, but then put absolute values everywhere and use a half. So now I can change my integral. The integral was over r x plus y dA, and now I'm going to integrate in the u and v. Notice that u goes between 1 and 3. That v goes from 0 to 2. Let me write du, dv, so I don't confuse the order. And then x, I have to transform the function. X is u plus v divided by 2 plus u minus v divided by 2. And I have to multiply by the Jacobian, which is a half. So that is the new integral that I have to do, but transformed. Okay? That simplifies a lot because that is just inside the parentheses, that is just u. So it's the integral of u divided by 2, and you can see in the solutions that this is just 4. Yes?
How did you know they were halves?
How did I know that these were halves?
Yeah.
I'm taking derivatives of this function here. So if you look at this function is a half u plus a half v. So when I take a derivative with respect to u, the derivative is a half. With respect to v, it's a half. This function has a half, but here it has a minus a half. So that's why there is a minus a half for
Wait,
y.
so that's the opposite one and that's the lower one?
There's a formula for the Jacobian. This is the derivative of u with respect to x, the derivative of u with respect to y, the derivative of v with respect to x, the derivative of v with respect to y. Yes?
When you're plugging in the actual function of the integral, like, can't you just use u since u equals x plus y?
That would have been better. Yes, yes. So x plus y, a priori, I'm using what they told me. But we had actually, as part of our work, we had figured out that u equals x plus y. So if you already knew that, then actually, yes, the x plus y, I could have just put in a u. But you do agree that it's u here, right? Yes. But yes, you could have saved a little bit of time just plugging u in there. Yes.
How did you get those two original choices?
How did I get these points? Or these points? These ones?
Yeah.
So for example, if you want to figure out what this point A is the intersection of the line y equals x and the line x plus y equals 3. Right? Then plug in the first equation into the second one, and I get that 2x is 3, so x is 3 halves, and y is the same as x, so it's 3 halves, 3 halves. So now I have 1 point. So every point is the intersection of 2 lines, so it's a little linear system for each point. All right. Other questions? Any other problems that you have? Yes.
Can you just start with one?
One. We're going to change the order of integration in a double integral. So let's figure out first what double integral they're telling me. They're asking me to do the integral of d of a function. I don't know the function. I don't mind. It's a double integral, so it's dA. And they want me to write it in the two different ways. What is the region D? That I need to know how to sketch. They are asking me to draw it in the first quadrant. The first quadrant, so it's just x and y are positive. And it is bounded by the y-axis. It is bounded by y equals x squared. And it is bounded by y equals 9. So the only region that makes sense, that is finite, is this region here. So this is D. Okay? I can set this integral as what we called a type 1 or type 2. I can go in x and integrate y from here to here, or I can go in y and integrate y from here to here. So I have to figure out how to set up those two integrals. And I need a tiny bit more information. I need to know where these two intersect, so I know what the limit of x is. I know the limit of y is between 0 and 9. So the limit of x, if y is from these two, if x squared equals 9, then x is plus or minus 3. But in this case, we're talking about positive values, so x is 3. So this number here is the number 3. So now I can set up the integral in one way and the other way. So let's do first, I run in x between 0 and 3. Then y will go, you see that y equals x squared is below y equals 9. So it goes from x squared to 9 in y of the function f. If I want to do it in the opposite order, I have to run in y first, and y will run from 0 to 9. And then the x goes from this function of x. This function of x is x equals 0. This function of x is equal to the square root of y. Okay? So, or this function of, sorry, this is, yes, from x equals 0 to x equals the square root of y. So that tells me then that x is running from 0 up to the square root of y in f of xy. Okay? Yes?
I just want to ask, I got a common habit of not putting like the fxy in there. Are you taking points off for that?
We are integrating that function. So if you don't put that in there, it means you are calculating the area of this region, which is not what this integral is about. So I think it does make a whole lot of a difference what function we're integrating over. And here f is just f. We're just trying to figure out what are the limits of integration. If it was clear you were leaving a gap, you know, and just, I don't know, put something like integral, whatever, dy dx, maybe, but just why not just be completely explicit and just write f of xy in there. Any other questions about this region? Am I jumping to number 2 or other number? 2. Okay? So we're going to calculate in polar coordinates this integral, and they want to evaluate it and all. So what is this region? It's a region in the first quadrant and bounded by the circle of radius 4. So if I draw 1, 2, 3, 4, 1, 2, 3, 4, it goes like this, and it has to be in the first quadrant, so this is my region. This is D. So now I need to figure out what are going to be my change of variables. R cosine theta, y is r sine theta, x squared plus y squared equals r squared. The radius here goes up to 4, so the radius can go up to 4. What are the bounds for theta? Pi over 2. Pi over 2 because we're only in the first quadrant, so the angle theta can only go up to pi over 2 because it's just a fourth of the whole range. So now I can just integrate. Can I? No, let's figure out also what that function is before I do anything. This function is the square root of 1 plus r squared, because x squared plus y squared is r squared. So the integral of d of that function dA is going to be in polar. Theta is going to go from 0 to pi over 2. R is going to go from 0 to 4. We are going to integrate 1 over the square root of 1 plus r squared. And I have to multiply by the conversion factor, which is r. The r, the theta. Okay? Thank goodness for that r, because otherwise this integral would be a lot more complicated. So once I have that, what I can do is, okay, integral from 0 to pi over 2, integral from 0 to 4 of r square root of 1 plus r squared, the r d theta. I can do a u substitution. Du is 2r dr. Therefore, this integral becomes, oh, by the way, what happens with the u, the values, or the limits of integration, when r is 0, u is 1. When r is 4, this becomes 17. So now it's going to go from 1 up to 17 of 1/2 du is, or du divided by 2 is r dr. So I get a half times u to the minus 1/2 du d theta. The change, this substitution changed the r, not the theta. And then if you integrate this, then you get the integral from 0 to pi over 2 of u to the 1/2 between 1 and 17 d theta, which is the integral from 0 to pi over 2 of the square root of 17 minus 1 d theta, and that does not depend on theta, so this is just the square root of 17 minus 1 times pi over 2. This 1/2.
Yeah.
When I integrate it, so the antiderivative of 1/2 times u to the minus 1/2 is u to the 1/2.
Oh, that was before you integrated?
Yeah. This I had not integrated, and then this is already integrated, but I have not evaluated the limits yet. No, there's like 2 camps of u substitution where you substitute everything, right? Where you substitute the limits of integration also, and so on. If you want you could come back. What you mean is in here, now substitute u was supposed to be 1 over the r squared. So now put the square root of u1 minus r squared and then put the original limits in. You can do it like that if you want. I prefer to do a clean substitution and bring the limit of integration also with u to the new variable. So just completely forget about the r. But that is up to you. No, it's not incorrect. As long as you keep track of like, okay, now I'm coming back to the r and evaluating in r values. All right, let's move on to spherical geometry. How do we integrate the solid E that lies within the sphere and above the xy plane in the spherical coordinates? So again, a sketch helps because this is a sphere of radius 5. 1, 2, 3, 4, 5. Like that, more or less. And above the xy plane, so this is just, I mean, this is just half a sphere. I don't need triple integrals for this, but they just want me to set up the actual integral. So what does this say? The region is with this base and then the sphere on top. So what are the limits of integration? Let's try first d theta. Again, there was a question before about the cone. Again, this is all around. It doesn't say it's just above the xy plane. I'm not restricted in octants in 3D. So it is, the theta goes all around from 0 to 2 pi. The phi is going to go only 90 degrees. It goes from here all the way to 90 degrees, not beyond it. So it is going to go up to pi over 2. The rho goes up to the sphere, which is radius 5. So I'm going to go in rho from 0 to 5. I am integrating the a volume. So in this case, I'm integrating the function 1. And I have to use my correction factor for spherical geometry, which is rho squared sine of phi. Okay? If you do this integral all the way, you get 250 pi divided by 3, which should be half of the volume of a sphere of radius 5. And you can check that works. Any questions of setting up a triple spherical? Yes. Good question. So if it is only in the first octant, the theta is just in the xy plane. So you can simplify your life and don't look at 3D, just look at the xy plane. If it was in the first octant, the intersection of the object would be here, right? And then you can see that theta can go from 0 to pi over 2. So if it was just, it would be a fourth of 2 pi. So it would go up to pi over 2. 2 pi divided by 4, which is pi over 2. Yeah. Let me quickly compute another Jacobian. So here the transformation is x is 4u plus v, y is u minus 2v. And by the way, to emphasize the point again, it's asking me to calculate the absolute value of the Jacobian, which is the quantity that goes in the integral when I actually do a change of variables, okay? So I'm going to compute the Jacobian, but then don't forget the absolute value. So the absolute value of the Jacobian will be the absolute value of whatever determinant I get here. The determinant will be the derivative with respect to u of x, 4, with respect to v, 1, the y with respect to u, 1, y with respect to v, minus 2. So that determinant is minus 8 minus 1 is minus 9, and the absolute value is 9. The Jacobian can be negative, but in the transformations, when we do the integrals, what matters is what is the size of the Jacobian. Okay? So in absolute value, what's the magnitude of the Jacobian is how much the transformation, when we change the variables, how much the transformation is changing areas. And by minus 9, it just means that actually it's transforming the area, but also doing some flip of the area. But the flip doesn't matter to us. What matters is that the area itself is moving. What was 1 unit of area, now it's 9 units of area. I have 5 minutes. So do you have any other questions?
So if the Jacobian is 9, does that mean it's 9 times bigger than the original? Or 9 times smaller?
It is different. It's just like the conversion factor of area differentials is 9. But now there's going to be different limits of integration. So it's not that the integrals are the same up to a constant by 9. The 9 is the correction factor. So at the end of the day, when you do all the integral, you have the right value. How would we compute this integral? They give me vertices 0, 0, 2, 0, and 2, 1, 2, 3, 4 over here. So the region I'm integrating over is this triangle here. I can set it up in 2 ways. I could go in x and then y, or I can go in y and then x. That's up to you. It just seems easier to go in x first and then in this direction because y will start at 0. So I'm going to integrate in this direction. So I need to know what functions I'm integrating over or what are the values of the limits of integration. This point was 2, 0, so the x coordinate runs from 0 to 2. And then what is this function over here as a function of y? So this is y equals 0, the x line. This one, let's see, this point right here was the point 2, 4. So the y coordinate is twice the x coordinate. So this line is the line y equals 2x. So now I know how to integrate in this region. This region will be the integral from 0 to 2 in x. In y will go from 0 to 2x in y. And I have a function to integrate 3x minus y dy dx. This is Cartesian, so there's no conversion factor. So it is just, there's no Jacobian. So that's the integral you have to solve. And if you integrate, I get 32 over 3. Yes?
Can you remind me in what scenario would in the integram, would it just be a function or if it would just be 1?
Yes. So they tell you, the problems either tell you, or it's not just the problems, like when we want to do an integral, either we want to find an area of a region, and in that case we're integrating the function 1. So whenever you integrate 1 over a region, either 3D or 2D, you get the area or the volume if you integrate 1. So whenever they say calculate the volume of the region, blah, 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 then that is the integral of 1. But if they tell you evaluate a certain integral because it's some function, then they will give you an integral that has a function, and they will tell you integrate the function f of x, y, whatever that is, over the region described in this way. So if they say area or volume, that's the function 1. If they just give you some other function, then that's something else. The difference is that in this case, I'm integrating over a region of a function. So you can think of, for example, if this region, if I try to compute the weight of a plate that has a different density, that the density is not homogeneous, if I want to compute the total mass of that, I would have to integrate over the density. So one way to interpret these functions, these integrals, is that I'm integrating a density function. All right. Good luck, everyone.